Welcome to Fundamentals of Artificial Intelligence. Today we are going to look at uninformed search. Usually in most of the AI techniques that we will explore, we will later look at using domain information or what is more commonly called heuristic knowledge, which would be under the category of informed search. However, as an introduction to search in graphs, we would love to look at uninformed search first. So what we will cover today is we will very quickly review problem solving as search, look at what we meant by state spaces. We will then formally introduce graph searching and introduce a generic searching algorithm. Thereafter, we will look at a couple of uninformed search strategies. First, the breadth first search, thereafter the depth first search, iterative deepening, uniform cost search, and then we will look at something called bidirectional search. Let's look at what we meant by problem solving as search. We define a state space that contains all the possible configurations. One or two configurations I have shown you. We would love to define all possible configurations of the relevant objects. We would then look at the initial state, that is, specify one or more states within that state space as situations from which we start. And then we define something called the goal state, one or more states that would be acceptable as solutions to the problem. And of course, we need to specify the operators, a set of rules that describes the actions or operations available. The state space is what is vital for formulating a problem solving domain as state space search. The state space literally consists of all possible configurations. This is also referred to as the problem space. For the 8 puzzle game that I have shown you little while ago, each tile configuration is a problem state. The 8 puzzle, we should note, has a relatively small space. Okay? There could be problems which would have huge state space, and we would look at how to search it in order to get to a solution. So let's look at problem solving as state space search, and this is the start node which I wanted all of you to take note of. This is as with 9 tiles here, one of them is blank, and you move the blank around to arrive at this goal position. Now, in the last class, we have looked at how these expansions can take place given the 4 operations. We will just look at the complete tree of solution. So, given this state, you could have 3 possibilities of moving the blank. So, the blank is here. You could think of moving the empty to the left. It could come here at this point, or you could think of moving it up to the center, or it could move it to the right. So, given the start S, these configurations of tiles are its successor nodes, successors, and we can keep on generating the successors. Like from here, we could get more successors by moving the blank to a newer configuration, like the blank could go up and one could come down. So, we could have 2 blank 1 8 6 7 and 3 4 5, and we could have another one which would be like 2 8 3 1 6 4. 7 could go this side, and I would have blank here, and I would have 5. So, we could generate all the successors from one node. But one thing to note here is that this point here, this node here is a repetition of what I started with here as my start. So, I would avoid getting expansions of these type of successors. Having said that, I would love to get all the successor nodes listed, and then the idea would be to look for a path that takes me through this space of successors to the configuration that I was looking for, and therefore this is line of expansions would be the solution to the problem that I was looking for. Now, if you look at this very closely, we can have a simile here. This can be thought of as a graph, and basically what are we looking for is, given a node, start node of a graph and a goal node G, I am looking for some path that takes me from S to G. So, problem solving as state space search can be abstracted to the mathematical problem of finding a path from the start node to the goal node or in a directed graph. So, let us take a look at what we mean by graphs and directed graphs before we proceed further into our discussion of problem solving a state space graph. You must have looked at graphs before, but for completeness, so let me put the definition here. A graph G comprises a set V of vertices and a set E of edges. The vertices as can be anything, but is most commonly a collection of letters or numbers. That's the representation. And the set of edges is a set of doubleton subsets of V. That is, E is a group of subset of A, B, where A, B belongs to the vertices and A is not equal to B. Usually the graph is denoted as a two-tuple G, V, E. So, if a graph is given and I know its edges, then we say vertices A and B are adjacent, and if there is an edge AB that joins them in the graph, and we call A and B themselves as the endpoints of the edge. Two edges that share a vertex, such as, let's say I have a graph here and I have A here and a B here, and that's one edge. I have another edge A and a C here, that's another edge. So, if I have AB and AC, here they are sharing a common node A, and then they are said to be adjacent to each other. So, I am more interested here in finding out the path in a graph. Like if you recall, we had this 8 puzzle tile configurations, and where I explored and really got these sort of structure there as I keep on expanding my nodes at every level, given the 4 operators of the 8 puzzle game to me, and from a given S, as I could arrive at a given G. I am more interested in finding out how did I come from S to G, or get to know what is a path. So, the notion of a path in a graph is intuitively very clear, but it is very difficult to pin down it formally. So, suppose I have a graph which is a set of vertices and edges, and I have k vertices. So, 0, 1, 2, 3 up to k plus 1, not necessarily distinct, and I have edges as E1, E2, so on and so forth up to E to the sub k, not necessarily distinct. Now, each edge EI is a group of vertices. The alternating sequence that I get of the vertices and edges, starting from the vertex V sub 0 to V sub k, is a path from V sub 0 to V sub k of length k. The length is the number of edges and it is not the number of vertices. So, for this path that I have highlighted here, the length of the path is 1, 2, 3 and 4. So, here is a 4 length path, and what I wanted to highlight was that this path is made up of edges E1, E2, E3, E4. So, alternatively it had vertices, let us call this vertex as VA, VB, VC. So, the path from the start to the goal for the given graph would be something like S, E sub 1, V sub A, E sub 2, V sub B, E sub 3, V sub C, E sub 4 and G. So that's the path that's in the given graph. What we are more interested when we are looking at graph search for solutions to given problems is what are called directed graphs or digraphs for short. Here again it has a set of vertices as V, but the set of edges is actually directed edges. So what are directed edges? Directed edges are ordered pair of elements of V. Put another way, if I have a graph of two tuple of V and E is a subset of V cross V, it is a digraph if these pair which I get are ordered pairs. So ordering of pairs in E to give each edge a direction, namely the edge AB goes from A to B. So here is an example of a digraph. I have a set of vertices A, B, C, D and pair of edges AB, AC, BA, CC, DC. So if these pairs are directed at arcs rather than just being edges as in the general graph that I was talking of, then what we have is a digraph. A tree is a connected graph with no cycle. So here if you go back and see the directed graph, here we have a arc that starts at C and comes back to C again. Or if you could see here, we go from A to B and then there is a path from B to A. Such a thing is called a cycle. So in a tree, we have a graph which is connected, but they do not have cycles. And this is something that we'll explore or in the remainder of this lecture. So graph searching for problem solving as state space search is to find a sequence of actions to achieve a goal, or as searching for paths in a directed graph. To solve a problem, we define the underlying search space and then apply a search algorithm. Searching in graphs therefore provides an appropriate abstract model of problem solving independent of the particular domain. And the type of graph we are searching here, one needs to remember, is usually a directed graph. So we are in now position to formalize search in state space. So let's define a state space. A state space for us is actually a graph of vertices and edges, where V is the set of nodes and E is the set of arcs. Here when I say nodes, the node may be a simple node or it could be a data structure that contains a state description. It could contain other information such as parent of the node, operator that generated that node from that parent, and other bookkeeping data. And each arc corresponds to an instance of one of the operators. So basically whenever we are talking of formalizing in search in state space, is we are looking at having whole of the state space converted into nodes with each operator giving me some instances that takes me to the other nodes. So finally we end up having such a directed graph, and searching in this directed graph for a path that brings me from S to G is what I mean by getting to the solution. For each arc in such a directed graph has a fixed positive cost associated with it corresponding to the cost of the operator, and each node has a set of successor nodes corresponding to all of the legal operators as that can be applied to the source node state. The process of expanding a node means to generate all the successor nodes and add them to their associated arcs. One or more nodes are designated as the start node, and then there is a goal test predicate which is applied to a state to determine if its associated node is a goal node. A solution in such a formal framework is a sequence of operators that is associated with a path in a state space from a start node to a goal node. And the cost of each solution that I am looking for is the sum of the arc costs on the solution path. So, if all the arcs have the same unit cost, then the solution cost is just the length of the solution or the number of steps or the state transitions that's involved. So, state space search under such a scenario is the process of searching through a state space for a solution by making explicit a sufficient portion of an implicit state space graph. Now, one needs to remember that we do not generate the complete graph when we are looking for a solution under this idea of problem solving. We keep on generating the graph as we keep on exploring for the solution. So, it is the process by which you search through a state space by making explicit only a sufficient portion of it, of an implicit state space graph to find a goal node. For large state spaces, it is important to realize that it is not practical to represent the whole space. So, you initially start with just the start node and then expand the start node S, its successors are generated and those nodes are added to the set V and the associated arcs are added to the set E. This process continues until a goal node is found. So, instead of having the whole state space graph as it is explicitly generated and then looking for a solution, the idea is to make explicit a sufficient portion of this as I go on expanding for nodes, and every node that I expand answering a question whether that is my goal node. If not, getting its successor nodes and keeping the process continuing. So, state space search is when each node implicitly or explicitly represents a partial solution path. In general, from this node there are many possible paths that have its partial path as a prefix. So, basically what it means is that when I am doing such a state space as exploration in a directed graph, I have come up to this point and then I keep on expanding beyond. But one needs to remember that whatever I have expanded up to this point, this still forms a part of the path. So, it's still the partial path is still there as a prefix for me. Beyond this there would be many alternate paths, but this one up to here, if somewhere the goal lies below this node, then up to here this is the partial path that's included already. So, how do we evaluate such search strategies? It's important to realize that we have many such searching techniques that we will discuss which are uninformed, but how do we evaluate such search strategies? There are four distinct matrices. One, we talk of completeness. Completeness is a guarantee of finding a solution whenever one exists. So, if a solution exists and if your searching technique can find that solution, and the technique is said to be complete. Next, we talk of time complexity, that is how long does it take to find a solution. This is usually measured in terms of the number of nodes that the searching technique expands. Next, we talk of space complexity, how much space is used by the algorithm. This is also usually measured in terms of the maximum size of the nodes list during the search. And then there is a question of whether this search technique is optimal or admissible. If a solution is found, and is it guaranteed to be an optimal one, and that is it the one with the minimum cost? If that guarantee is there for the given searching technique, then it's said to be optimal. We will now look at these searching techniques and then look at the evaluation of these techniques along these four matrices. So what are the important parameters that one needs to really look at before we go into looking at the search techniques and evaluation of them is these three interesting things that needs to be remembered. We talk of a number of successor of any state, the maximum number, that's called the branching factor. Then we talk of the length of a path in the state space is the minimal length, which is the depth of the shallowest goal, or that's D. So we need to understand and something about D and something about B. So if I have a node that's expanded every time into 2 successors, so here my branching factor is 2. If my goal lies here, that's the depth of the minimum length of the path to the shallowest goal, then my D is 3. And I could have a maximum depth which goes on, it could be infinite, and that maximum depth of the state space is M. So given these parameters to me, and given the idea that we could search a directed graph to arrive at from a given and state to a given goal, we look at a graph search procedure. So even before I write the algorithm for the graph search procedure, I would like to highlight that what we literally do is we have the start node S, and we have its successors. Let's call this successors A and B. So we create 2 lists, one called the open and other called the closed, and we first put S in the point where it needs to be expanded. So we create a list called open and we put S in the open list. So we put S here consisting solely of the start node, and then we pick up S for expansion. So we pick up S, and what we want to really check now is that is S as the goal node itself. If not, we generate its successors. So if S is the goal node, we have nothing to do. We must come out and exit. That's what is a check here, by saying that I create a list is called closed, that's initially empty, and then if there is nothing in open, I have to exit with failure. But otherwise I select the first node on open and remove it from open. I take it away from open and push that node in close. Now why do I do that is a way to remember that S has been expanded. So then after that, what I do is I generate the successors of S. So the successors of S here are A and B. So I take A and B and put it in open. And next, when I look for an expansion, I take the node from open, so A comes to me. Now one needs to remember that how I add A, B onto the open list will depend on what criteria do I really follow in order to really arrange this. Is later on we will see that if I am doing a breadth first search, I would see that everything is added to the end of the list. If I am doing a depth first search, I would add it to the beginning of the list. Okay. So basically you create a list called closed that is initially empty, and you take the first node on open, you remove it from open and put it on close, and then if n is goal node, we have nothing to do, we exit it immediately. Else what we do is the following: we expand the node n, generating the set M of its successors. So we install them as successors of n in the open list. So add these members of M to the open list and then expand them further. Now if each member of M is already in G, then we can decide whether we want to redirect its pointers, or if each member is already in close, that means one of the successor is already been expanded, then we can redirect its descendants whatever are there to that pointer, else we will ignore that node to be expanded further. So, how do we reorder the list open, and is very, very important to understand, and the type of technique that we will have in the graph search. So, they are either according to some arbitrary scheme if it is uninformed search, and according to some heuristic merit if it is a informed search. Today our concentration would be only on looking at arbitrary schemes of arrangement and of the successor nodes in the open list.